gonna look the first topic for kinetics, okay, collision theory and activation energy, the ideal gas equation. So objectives of this topic is recall and be able to apply the ideas from earlier work on the states of matter in simple collision theory, be able to apply the ideal gas equation, the molar volume, to reactions involving gases. So rates of reaction. So before you start, it will be helpful to know how the energy changes during chemical reaction, know the basic ideas of kinetic theory. So first of all, collision theory. Okay, collision theory states that particles must collide before a reaction can take place. So imagine two cars. When they collide, they release some amount of energy. Okay, so this energy in chemical reactions is called activation energy. So reactants must possess at least a minimum amount of energy, so to activate the chemical reaction. Okay, but not all collisions lead to a reaction. Okay, there will be some collisions that are not which do not collide properly, so that they will not release some energy. Okay, so particles must approach each other in a certain relative way. So correct, we can say it, they must collide in correct orientation. So according to collision theory, to increase the rate of reaction, you need more frequent collisions, increase particle speed or have more particles present, and more successful collisions. Okay, give particles more energy or lower the activation energy. Okay, so this is collision theory. Okay, so please remember that you must have frequent collisions and successful collisions, so that when they collide, they release minimum amount of energy, which is activation energy, and they must collide in a certain way, so in a correct orientation. So this is collision theory. So it's actually from the previous studies. So next, ideal gas law. So in ideal gas law, we say that all gases are ideal. So we think that all gases are in ideal fashion. Okay, so to describe every gas, we need to have four variables. Temperature, pressure, volume, and number of moles of gases. So we can see some relationships between these values. For example, Boyle's law says that pressure multiplied with volume is constant. So it means pressure is inversely proportional to volume. Okay, so as you increase pressure, you decrease the volume. Next, Charles law. So V1 divided by T1 equals to constant. So that means Charles law concludes that volume is directly proportional to temperature. Next, Gay-Lussac's law. So here is the same, but here we have pressure. So pressure is directly proportional to temperature. And combined law, if we combine these laws, we can see that pressure multiplied by volume divided by T is constant. From here, we can show that we have ideal gas law. So here, P stands for the pressure. P stands for the pressure. Okay, V for the volume, N is for the number of moles, R is gas constant, which is constant. So this is constant. And temperature. Temperature, we use the unit for temperature is Kelvin. Okay, ideal gas equation. So in order to use this ideal gas equation, PV and RT, you must know what's gas constant. Okay, so gas constant is here we have two different gas constants, which are 0.082 liters multiplied by atmosphere divided by mole Kelvin, and we have another gas constant 8.314 joules per mole per Kelvin, or we can use liter multiplied by kilopascal. Okay, it depends on the question what kind of values you are given. If the pressure is atmospheric, so it's better to use this one. If your pressure is given in the kilopascal or pascal, it's better to use this one. Okay, but mostly in our curriculum we use this value. Okay, so now let's move on some examples. Okay, so some problems. What pressure is exerted by 0.75 moles of a gas at 25 degrees in a container with a volume of 1.5 liter? So we must use our formula PV equals to nRT. So we are calculating pressure. So pressure, we rearrange formula, so it means N multiplied by R multiplied by T divided by volume. So N is given 0.75, R, so here let's calculate in the kilopascal, so it will be 8.314 kilopascal liter divided by mole and Kelvin. Volume is given 1.5 liters, and temperature is 25 degrees. Again, 20 degrees Celsius degrees must be converted to Kelvin. So to convert Kelvin, we just add 273 and we get 298 Kelvin. Just plug this form, just plug these values, so we get 0.75 multiplied 8.314 multiplied by 298 and divide by volume, which is 1.5. So let me calculate this. So 0.75 multiplied 8.314 multiplied to 98 divided by 1.5, and we get the value of 1239. Okay, so 1239. So this value is in pascal, so in kilopascal it will becomes 1.2 kilopascals. Okay, next question. Find the value of a 0.85 moles of gas at pressure of 520 pascal and the temperature. Okay, so let me, so here, no, so sorry, we miscalculated. So this value is in kilopascal. Okay, so 1239 kilopascals. Next, find the volume of 0.85 moles of gas at pressure of 520 pascal and the temperature 15. So again, PV and RT, we need to find volume. Volume is equals to pressure divided by nRT. So pressure is given 520. This is in pascal. Okay, so this is in pascal. We need to convert to kilopascal. If we convert to kilopascal, I just put 0.5, so it will be 0.52 kilopascal. So here kilopascal divided by number of moles, 0.85 multiplied by 8.314 multiplied by 15 plus 273. Okay, so here let me calculate. So divide 273 plus 15, 288. So here we get a very small number, which is 2.55 10 to the power of minus 4 liters. So if we multiply by 1000, we get 0.255 milliliters. Okay, so next question, how many moles of gas are present in a sample of at 700 pascal, 333 Celsius degree, and occupying a volume of 452 milliliters? Okay, so again, PV and RT, just write down the formula, and you are finding number of moles. So rearrange the formula, PV divided by RT. So pressure is given, so 700 pascal, so it will be 0.7 kilopascal. Volume 452 milliliters, so it will be 0.45 2 liters. Gas constant we use 314. Temperature is 333 plus 273. So for temperature we have 606 Kelvin. So we just use this formula, so 0.7 multiplied by 0.452 divided by gas constant 314 multiplied by 606. Okay, so let's calculate. 7 multiplied divided by this, and again we get very small, 25 10 to the power of minus 5 moles. So this is how we calculate, we use ideal gas equation.